My name is Ivanei Pinheiro. I'm postdoc at Sepetro, and I'm part of the FunWorks team. And today I will present about the experimental evaluation of model wax diffusivity by NMR. So here I will present about some experimental results, diffusivity, that we use in nuclear magnetic resonance to determine the diffusivity. So first, of course, that wax deposition, it's a big problem for the oil industry, and there are some wax deposition mechanisms that are considered in the literature and also in the oil industry, like molecular diffusion, phase transition, Brownian diffusion, for example. However, they must use it, they must consider from the literature and also for the oil industry is the molecular diffusion. So today our focus will be in this model. Okay. When we consider the molecular diffusion as a method to form a deposit, for example, we have some important points here. The first one, it's about uh, temperature gradient, and the other one, it's about the concentration gradient, and also the diffusivity. That is our focus today. And speaking about the diffusivity, the important point is that the literature consider that the correlation or the model that is used to calculate the diffusivity works just for a limited set of conditions. And two correlation or two models are used, basically two are used in the literature and also in the oil industry. That hydrochemias is one and Y exchange is other. It's a simple correlation, it's a simple model, and they consider both consider just the temperature, viscosity, and molar volume in both cases. So our idea here is to determine the diffusivity, experimental of course, and to compare this experimental diffusivity with this correlation like hydrochemias and Y exchange model, for example. So a simple way to determine the diffusivity is using nuclear magnetic resonance or NMR. In this case, we can determine the diffusivity from the relation between the relative intensity with the field gradient that's applied in the sample. So it's a very powerful technique, and we can include separate molecules if you have some mixture, for example, using this technique. So if you consider that you have, for example, 3 molecules in the mixture, I can determine and separate the diffusivity for these 3 components in the mixture. It's very interesting because when we consider oil, for example, we have a combination of molecules. So here we bring some literature data about the diffusivity, and this literature data was obtained. This data, sorry, was obtained for by different ways using, for example, NMR, like the first one here, or using a combination of experimental tests like a cold finger and ESC, for example, like the second one here. And we can see in the first one that the correlation, the hydrochemias correlation and Y exchange correlation can't predict exactly the real diffusivity, for example, the diffusivity experimental, for example. And we can see the same behavior in the second in the second data here, again we can see that like Chang or hydrochemians that can't predict the diffusivity. In this case, the test was did using two different oils and the same behavior was observed. We bring again other experimental tests about the diffusivity. In this case, it was used the Taylor dispersion method, and the authors in this case measured the diffusivity of the molecule with 18 carbon and 26 carbon in ethane. And the black points here, it's about the experimental results obtained with the Taylor dispersion method. And the red line here, it's about the correlation hydrochemians. And again, we can see that the correlation can't predict the real diffusivity, for example, or the experimental diffusivity, for example. So independence on the method used to determine the diffusivity, hydrochemians or white chain correlation can't predict the real or the experimental diffusivity. So think about this result. Our focus here is determine the molecular diffusion using nuclear magnetic resonance. So for that, we use two kind of paraffin, two kind of wax, macro wax and micro wax, and we use as a solvent toluene, and we also use some standard molecule with 20, 30, and 40 carbons in this case. We use chromatography in this case. The idea it was to determine the carbon distribution for the micro and the macro wax, and for measure the diffusivity we use NMR in different temperature. Okay, so here we have a result about the chromatography, and you can see that the micro wax or the micro paraffin showed a high carbon distribution here, so a higher molar mass compared to the macro. It's important information because it will impact directly on the diffusivity. So here we have some results diffusivity. In this case, it's for icosane, the molecule with 20 carbon, and we can see here that the experimental result is different, very different of the model. In this case, the hydrochemia's model, the red line here, and we can see again the effect of the temperature in the diffusivity here. And when we compare the experimental results with the correlation of hydrochemias, we can see that the error is higher and begin something like 70% again, and can reach almost 90%, for example. We also measure the diffusivity for the molecule with 40 carbon here, and the same behavior was observed here. Again, we have a red line for the hydrochemia's correlation, and the black point is for the experimental diffusivity using NMR. And we can see again a same range of the error here, independent on the temperature. So here we just compare the experimental diffusivity for the molecule with 40 carbon and the molecule with 20 carbon in black here, black points. So we can see that as the molar mass increase, the diffusivity is reduced independent on the temperature used here. And we again evaluate the effect of the solvent here in the diffusivity. So in this case, we use as a solvent eicosate, the molecule with 20 carbon here. And we can see that for solvent that has the same viscosity, for example, octane and toluene, as you can see here, the diffusivity is almost the same. And if we change the viscosity, like a chloroform, for example, we have a significant change in the diffusivity. So it confirms that the viscosity it's a very important parameter for the diffusivity. So here we measure the diffusivity for a combination molecule. So we have a molecule with 12 carbons and 50 carbons. And we can measure the average diffusivity for this set of molecule here. And again, we can see that the hydrochemias model, red line again, can predict the experimental diffusivity. So, and the error again is still in the same range. So here we compare the effect of the average diffusivity. So in this case, we calculate using hydrochemias. We calculate the diffusivity for all molecules in this set of molecules, and we use the average diffusivity for this case. And in the blue line here, we just consider an average of molecule weight in this case. So we calculate the average molecule weight here, and we apply it in hydrochemias. And we can see that when we consider the molecular weight, the model the result in the model, the hydrochemical result is better than if we consider the average for each molecule that we have in the mixture, for example. So this way is also considered for the oil industry and the literature. We also tried and we also measured the diffusivity for the macro wax, the macro paraffin, and we have again the same behavior that we observed in the other solutes used here. Again, the range of the error is almost the same. The same behavior was observed in the micro wax, sorry, and the range of the error in this case increased a little bit. So here we compare how the diffusivity, how the experimental diffusivity and the diffusivity obtained by hydrochemias will impact in the thickness of the deposit, for example. And we did it using two ways: the equilibrium model and the film mass transfer also. So here we have here we have an equilibrium model. The red line here it's considered the experimental diffusivity, and the green line it's considered hydrochemia's diffusivity. And we can see that the difference is very significant when we use the experimental or when we use the hydrochemia's correlation diffusivity, for example. The same one, so the same behavior it's observed in the film mass transfer also here. So the final consideration is hydrochemia's overestimate in all cases the diffusivity. The temperature, viscosity, and the molecular weight are parameters that directly affect the diffusivity. Using the average diffusivity of each molecule in the mixture increase the prediction error of hydrochemias, and NMR technique shows a promise for the diffusion measurements of simple systems. Our next step here is propose an adjustment based on the experimental data, evaluate also the crude oil diffusivity, and apply the fit and compare with crude oil diffusivity data. Sorry. We would like thanks our partners like Unicamp, PEC, ANP, and especially Brazilian Bioscience National Laboratory when we have been using the NMR. Thanks a lot.